Yeah, hello. Hello. So I would like you guys to unmute and speak so that I can check whether I'm audible or not. So because during the sessions I'll not be able to check the message box. So it would be good at least if few people unmuted and spoken between. Hello. Hello.
Yeah, hello. Good evening. You're audible. Yeah.
Yeah, fine, fine. Okay, so in that case, let us start the first tutorial session on the course Fundamentals of Electronic Materials and Devices. So before we move on to the actual problem solving part, I'll give you a brief intro of what is the intended purpose of these sessions and how this would be beneficial for or your overall progress during the course, and as well as how it would help you in the solving the assignments as well as the final examinations that come. So eight people have joined today, not eight people, excluding me, it will be seven people. So I request that at least most of you attend all the sessions so that suppose you get few doubts in assignments or so, we can solve those and eventually those will add up to your final marks. So before we start, can I know can you just open your chat box and type down what background you're from so that we can plan the course accordingly in a way that everyone understands. So if you could please write the back like what you are doing and what you want to do with the course, what is the intention of attending these sessions and what is your background. So if you guys can take a few minutes to type that down, that would be very good. And if anyone wants to unmute and speak, that is also good. Hello.
Hello, good evening.
Yeah, good evening.
Um, my name is Dr. Jagdish Babu Bellam, working as assistant professor in the Department of Physics at Madanpalli Institute of Technology and Science, Madanpalli.
Okay.
So I have done few courses on electronic materials, and recently I have completed IC fabrication course by the same professor, and I had to complete two more courses to complete my domain certificate on electronic materials.
Okay.
So the purpose is to complete the domain certificate, and the lectures are useful to understand the basic concepts. My background is MSc Physics and Doctor of Science in Electrical Engineering,
Okay.
postdoctoral fellowship from University of Limoges, France.
Okay.
From 10 years, I'm working in this institute.
Okay. So
Yes.
you're well versed in semiconductors and stuff, and you want to do this course so that you get credits for your domain completion, right?
Yes.
Yeah. Okay. Thank you. So what about the others? So the idea is that this is basically an interactive session. So when you are asked to speak up stuff like this or ask questions, so it, it would become more useful if you guys can give your input. So now I've asked people which background you're from. So if you give me that, I'll be able to make the contents in such a way. Otherwise, I'll be speaking from a POV that the course itself is prepared. Suppose a person is from a very different background, that person might not be able to grasp compared to a person who knows semiconductor very well. So in that case, if everyone would just take at least few seconds and write down your backgrounds, that would be really great. So we have Venkateswaran, Grace, then Neha, Nikhil, Sana, Bhavan, Sarala, Varshini, sorry, Varshini, I think, and Vidya Sagar. So if you guys could just, yeah. Department of Physics. Okay, so you are also from a physics background, and but I hope that you know semiconductors quite well. What about the others? Please, everyone, please tell me about your background. Okay, somebody has unmuted.
Hello, good evening, madam.
Yeah, good evening. Hello. Yeah.
Myself Sunil. I am from Nandyal.
Okay.
Currently, I am studying diploma second year.
Okay.
This is the first attempt to join in your class, ma'am.
Okay, and you are well, like you know semiconductors, or you are beginning from like
I am
scratch?
beginning.
Okay, so you want to like basic understanding of semiconductors and how they work and so on. So,
Recently I joined, ma'am, so I didn't attend the classes.
it's fine, it's fine. Yeah.
Okay, ma'am.
Okay, thank you so much.
Thank you.
So the registration for certification exam is open right now. So people who are intending for just attending the course and just understanding part, they need not register for the examination. But people who want to use it as credits, or people who you want to get certified in this, you need to go through a certification exam. So the registrations are open right now. So you might have received a mail from NPTEL regarding the same, so please go through the guidelines mentioned in the mail, and those who are willing to write the examinations, please register as soon as possible. And it's better that you guys don't wait till the deadline. Suppose there is some issue with your login credentials or so and so, then again you'll have to mail the authorities and then wait for their response. And so, yeah. So Nikhil, yeah, you're studying MSc Physics, okay? Okay, so you have like you know solid state physics and semiconductors, I guess. Okay, fine, fine. Yeah, very cool, Nikhil. Thank you so much. And then simulation physics. Okay, okay. So I think like quite a few of you are from physics background, I understand. So in that case, like at least a basic course in semiconductors you might have taken somewhere along your career. So in that case, I think at least the first few lectures until we actually go to devices, it will be quite easy for you to grasp. And during the sessions, please keep note that every week content will be released. This is an 8-week course, and every other week there will be an assignment submission. So please keep track of the dates of submission, and as much as possible, watch the videos in the same week itself. Otherwise, for completing the assignments, you will have to take a lot of time in making up the videos in a continuous stretch. Yeah. So then we have Sarna. Okay. Okay. Department of Physics again. Okay, fine. Yeah. Thank you so much. Yeah. So with that, I think we'll move on to today's not questions. So first, we'll see a brief overview of the course, the contents, the professor, and then what we are intending using these sessions. Then we'll solve a few questions. And since this is the first session, I don't want to keep it like going on for 2 hours. This is just the intro. I don't want to bore you guys. So we'll try to wind up as soon as possible. So I hope the presentation is visible. So can anybody unmute and tell me whether it's visible or not? Like I can't see the chat. I know I can hear the pop-ups, but I cannot see the messages. So like during, hello, sorry.
Yeah, it's visible.
Yeah, okay, thank you so much. So, this is the first tutorial session, as I mentioned, on fundamentals of electronic materials and devices. So, actually, two courses are offered in this particular field. That is, for this is the first course in the year, fundamentals of electronic materials and devices. Following this, in September, we have another course that is fundamentals of electronic device fabrication. So, in this course, we will see semiconductor basics, followed by like devices like MOSFETs, JFETs, transistors, and so on and so. But in the second course, that is electronic device fabrication, we will be seeing clean room designs, how the manufacturing of such wafers or semiconductor devices happen. So this is an 8-week course, and the second course is a 4-week course. So people who want to follow up on their knowledge of semiconductor materials, they can opt for the second course as well, and it will be offered in the September cycle. Right? So speaking about me, I am Sandra Krishnan. I am a research scholar at IIT Madras in Soft Matter and Complex Fluids Lab. I work on ceramic membranes, photocatalysis, and biomaterials. And as part of my BMRF tenure, I'm supposed to host tutorial sessions every week. And I've opted for this NPTEL course. I've taken up this course past 3 times as well. So everyone, please take note of my email ID. So for this NPTEL session, you have something known as the discussion forum. If people are familiar, you have something known as the discussion forum where you can post your questions and queries or doubts, whatever. that will be handled by a set of TAs. Other than that, if you have any personal query related to the course or anything related to PhD and so, you can mail me in this particular mail ID. So I request that all of you at least take a picture or like note down this mail ID somewhere so that you can contact me and I'll be available on this mail ID for your queries. So moving on to the course details, this is offered by Professor Parshuraman Swaminathan, who is an associate professor in the Department of Metallurgical and Materials Engineering at IIT Madras. And this is the course plan. So in week 1, that is today's contents, we'll be focusing on energy bands and solids, semiconductor band gap information, like basic stuff. Following that, we will move on to intrinsic semiconductors. This will be followed in week 3 by extrinsic semiconductors, Fermi level variations, conductivity, etc. In week 4, that from week 4 onwards, it goes like a bit in depth, like metal semiconductor junctions, introduction to PN junctions, and so on. So then we'll apply bias to PN junction, what happens during junction breakdown and water heterojunctions, and so on. So week 6, 7, and 8 will be on the electronic devices, that is transistors, MOSFETs, then optoelectronic devices like LEDs and lasers, and finally we'll conclude with the hot topic of the century, that is photodetectors and solar cells. And in each week you will have contents released in the NPTEL website. Along with that, you will have assignments, you will have practice questions, and we will be solving a few such questions here as well. And these questions will be similar to the ones you will be getting in the assignments as well as in the exams. And most times what happens is after the 8 weeks are over, there will be one additional live tutorial session, that is to help you with the exam, that is a revision session also we will be hosting. So for this course we have live tutorial sessions every Tuesday from 7 p.m. to 9 p.m. and the link will be same. So I hope that all of you will join every week. So basically, we know that NPTEL courses, few people are watching lectures, you don't have any interaction going on. Suppose you have a doubt coming up in the material or you are stuck somewhere, there is no like interaction or a person whom you can contact and ask doubts. So the goal of hosting such a session is that it will be a more engaging learning process and you will get help with the practice assignments as well. Since we are solving questions here, you will receive tips and tricks of how to you score better in your assignments as well as in your doubt in your examinations. And one more thing is that in addition to these doubt clearing sessions, suppose if many people in a particular course, like particular week, feel that suppose the topic is not very clear, like even though you watch the lecture you feel that the topic is not very clear, then if you request me through mail and if I feel that okay, it's a valid reason, then we will be able to host topic discussions as well. That is one more thing. So in case you any difficulty you face with that particular course, now the technical part of the course, I would say, not the administrative part like login credentials and so on. So like technical details, content related doubts or assignments, etc., you can contact me either through these live sessions or in the mail ID. And one more thing is, suppose you have a doubt in the submission assignment, I will discuss those assignments after the submission deadline is over, because I can give you hints, but I'm not allowed to solve questions prior to the submission deadline. So once the deadline has passed, if you have doubts, we can solve the question in class so that it will help you in your final examinations. So before we want, and one more thing from the beginning itself, be on track, see the assignments and the videos as much as possible in the same week itself, and practice using online calculators. Like, well, so during these doubt clearing sessions, what happens is most people will be using their normal calculators, and once the exam comes, they'll have difficulty using the online calculator. So everybody, please download the online calculator, and during the practice sessions itself, try to use them such that you don't feel that transition difficulty later on. So any doubts do you have, like what all I've spoke so far? Do you have any doubts in that? Like you have any questions popping up or any doubts, you can ask now. Anybody, any doubts like regarding timing or any requests or anything? Guys, please, you can unmute. If you don't have anything, then we can move on to the questions. Any doubts, any questions, anything? I think not nobody is responding. Anything in the chat box? Let me check. Like, shall we move on to questions, everyone? Hello? Hello? Okay. Yeah, like guys, try to unmute and speak because otherwise I'll have to switch between the window and so and so. So please try to unmute and speak. And in the question answer sessions also, please try to be on your foot and try to answer, like speak up. It's okay. And I'm just a student like you guys, so it's not like a faculty is talking or some big person is talking. Even if any kind of doubt, even I might be getting doubts in such topics. So it's not like somebody is going to like scrutinize you for like asking anything. So anything you can have, even if it's a like vague thought, you can open up and speak, and like you can brainstorm during the talking process itself. So everyone, please, I'm requesting again and again, unmute and speak during the session. Yeah. So, first question is the empirical observation made in 1965 that the number of transistors in an IC doubles every 24 months is called dash. So, in most of the questions in assignments and final examinations, you'll be getting questions like this. So, this is a very direct statement related question from your week 1 contents. So, some scientists made an observation in 1965 that the number of transistors in an IC doubles every 24 months. Who was it? You have Treider's law, Moore's law, Haigh's law, and Gates' law. So, can anybody unmute and tell me what is the answer to this question? Like anybody?
Moore's law.
Yeah. So, that is the answer to the question, Moore's law. I hope it's a clear statement. Like Moore's law states that the number of transistors in an IC doubles every 24 months. So next is an even direct question. I would say the nature of chemical bonding in silicon is covalent. What is the nature of hybridization of the material?
SP4?
Anybody else? Okay, one person has said SP4. Any other, or any other person has any other answer?
SP3?
Yeah. So one person has said SP4 and one person has said SP3. So the answer is SP3. And one more thing, for people who make notes while seeing the assignments, it's not like you have to answer from your memory. So people who have made notes, you can open your notebook and then check if you have noted down these things, and you can refer an answer as well. Suppose if I'm asking a general question, suppose something like Moore's law, you can even use the online sources and then see what Moore's law is and then answer. It's not like you have to like answer suddenly from your memory and so on and so. So the nature of chemical bonding in silicon is covalent and it is an sp3 hybridized material. So next is, which of the following are not n-type dopants for silicon? Note that more than one answer may be correct. So we have four materials here: phosphorus, aluminium, bismuth, and gallium. So out of these, which of the following are not n-type dopant? So basically an n-type dopant is something that when added to an semiconductor material, it gives electrons, additional electrons as carriers to the material. So which of the following are not n-type materials? So it should be an electron deficit element. So you might have like understood based on the L, like the column in which they come. They can be either p-type dopants or n-type dopants. So which of the following are not n-type dopants? Like group 3, group 4, group 5, you might have understood based on that. Which of the following are not n-type dopants?
Aluminum and gallium for this N-type dopants. It is not.
So basically silicon, it comes in which group? So silicon, can anyone tell me silicon comes in group 3, 4 or 5?
Group 4.
Yeah.
Silicon comes in group 4, aluminum in group 3, phosphorus in group 5.
Yeah, so basically how that is how you identify it. So here they have asked for group silicon. So silicon is basically a group 4 element, and suppose you have something more than that, like group 5 elements will act as an n-type dopant because it will impart electrons to the material. Suppose we are in the other case adding a group 3 material, like say aluminium, what happens is that it will be electron deficit and therefore it will transfer holes as charge carriers. So in that case, which will be the answer here? Bismuth and gallium will be the answer because they have asked not n-type dopants for silicon. Is it clear? Yeah. So next is in an intrinsic semiconductor, the number of thermally generated carriers in the conduction band is dash the number of holes generated in the valence band. So it is an intrinsic semiconductor. Intrinsic semiconductor meaning that first, can someone tell me what is an intrinsic semiconductor?
Ma'am, pure semiconductors.
Yeah, something that is not having any impurities.
Yes.
Yeah. So in an intrinsic semiconductor, what is the ratio of thermally generated electrons in conduction band and holes in the valence band?
Ma'am, they are equal to each other.
Yes, that is because, can someone tell me why? Like any reason you can allow to why this happens?
Because no impurity is added.
Yeah. If we are not using any external impurities, it is just heat generated electrons and holes, right? Therefore, the number of electrons in conduction bands will be equal to the number of holes generated in the valence band. So is that clear?
In question number 3,
Yeah.
aluminum also not n-type dopant, no?
Yeah, like yeah, if based
So,
on the group number, yeah,
so the answer should be B, C,
B,
D.
B, C, D, yeah, like that is why they have mentioned more than one answer
More
here.
than one answer.
Yeah, yeah. Is it everything clear? Okay. So next is complete the following sentence. When n atomic orbitals in a metal overlap, they form n molecular orbitals which have n energy states which can accommodate dash electrons. So molecular orbitals theory, if you have gone through weak contents, you might have studied. So when atomic orbitals overlap, they form something known as molecular orbitals. And eventually they merge into energy states, which gives rise to the conduction band and valence band. So each energy states has how many electrons? Like if you have n energy states, how many electrons can they accommodate?
Two n electrons.
Yeah. Any other answers anybody has? Yeah, it will actually accommodate 2n electrons and such that one more law will be there, right? They should be of opposite spin. Can anybody tell me which law that is?
Pauli's exclusion principle.
Yeah. So I hope it's clear. It's 2n electrons. So next is the derivation of density of states for an FeG metal involves calculating the number of available states per unit volume. But each state can accommodate more than one electron. Name the property that makes this possible. I've just given the answer to this. Someone has like mentioned about Pauli's exclusion principle. So in that case, can anybody tell me the answer to question 6?
Ma'am, spin.
Yeah. Any other answers? So basically, Pauli's exclusion principle tells that no two electrons in an atom can have the same full quantum number. So finally, at least the spin, that they should have opposite spin. So while deriving FEG, that is density of states for an FEG metal, we need to calculate the number of states available per unit volume. And the calculation is based on the fact that electrons of the opposite spin should be accommodating these available states. So next is something you have to solve and give the answer. What is the density of states for an FeG metal at an energy of 3 electron volt? And your answer should be in joule inverse meter to the power minus 3. So you are asked to calculate the density of states of the metal and the energy is given as 3 electron volt. So can anybody please take your time, like all of you please try to solve, and can anybody give me the answer? Yeah, for now you can use your normal calculators and you can refer to the equations if you have noted down. Density of states equation you might have noted down. So using that you can find out. Density of states, you have to find out. The final answer should be in joule inverse per meter cube, and energy of the FeG metal is given at a value of 3 electron volt.
Ma'am, I got option B 7.3 into 10 raised to 46.
6. Okay. So let's wait for the others. One person has told us answer as B. So can the others also try and come up with the answer?
7.344 into 10 to the power 46.
Okay, one more person. Anybody else? Yeah, two people have answered 7.3 into 10 to the power 46. So others? Anybody else got any other answers? Yeah, so in that case, it is given that energy is equal to 3 electron volt. And to begin with, we have to convert, since the final answer is in joule inverse per meter cube, you have to convert electron volt into joules in the equation itself. So G of E, that is density of states for an FeG metal, will be 8 pi root 2 Me to the power 3 by 2 root of EF divided by H cube. So here we have Me, that is mass of the electron, as a constant, and H flux constant is also a constant, and 8 pi root 2 is also constant. Basically you have to find out the root of EF. So is this the equation that you had used to like arrive at 7.3 into 10 to the power 46?
Yes, ma'am.
Yeah. So for others, please take a note of the equation. So basically GE will come as this. So when you condense the equation, it comes to something like 8 pi root 2 ME by h square the whole power 3 by 2 root of EF. And while substituting, so here we can see 8 pi root 2 is a constant. Then if you see here, we have Me, that is mass of the electron, as 1.9 into 10 to the power minus 3 divided by Planck's constant, that is 6.626 into 10 to the power minus 34 of the whole square, the whole power 3 by 2. And whenever you're substituting any constants, please take a note of the final, like if everything is in SI, then you'll, since here it is in SI, you'll have to go for the SI value of h square. One thing is you can do like that during the solving part itself, you can convert them into SI and then convert, or the other thing is eventual, or you can get the final answer and then convert the final answer into the SI unit. And sometimes it need not be that the answer will be given in SI units. So according to that, you'll have to substitute. And here, if you see, we have to convert 3 electron volt into joules. So we multiplied 1.6 into 10 to the power minus 19. And we arrive at the answer of, so sorry, this is 10 to the power 46. This is a typo from my side. So basically GE is 7.3 into 10 to the power 46. So let me correct it on the fly.
Also, mass of the electron 9.1 into 10 to the power of minus 31.
Yeah.
It is given as 1.9.
Yeah, that also should be converted to. Yeah. So is it clear? And I think you have similar questions in your assignment as well.
Is it a typo error? Me, mass of electron.
Sorry?
Mass of the electron is 9.1 into 10 to the power of minus 31.
No, it's 10 to the power 9.1 into 10 to the power minus 31 kilograms. That is the mass of the electron in SI units.
Yeah, it's
Yeah.
9.1, no? Not 1.9.
Not 1.9. Yeah, that is also a typo. So yeah, I just noted now. Yeah, here also. Okay, I hope this is clear. Then we can move on to the next question. That is, the resistance of a copper wire is 2 microns. If the length of the wire is 10 centimeter and the dia is 1 mm, what is the resistivity? And your answer should be nano ohm meter. So choose the nearest value. Sometimes the value that you arrive at and the values given will be somewhat like there will be a minute difference. So in that case, you'll have to find the or choose the nearest value. So resistance is given, length, dia, and resistivity is given. It is like the basic equation that you use in physics. So if you know the relation between resistance, resistivity, length, and area, then you can directly substitute and find out.
Hello, ma'am.
Yeah.
It's option B, 15.7 N ohm meter.
Okay. Yeah, one person has got the answer as B. What about the others? Yeah, anybody else? Any other answers? Any other answers? So basically, we know that the resistance and resistivity are known. We have R is equal to rho into L by A. Here we are asked to find out the resistivity. Then R into A divided by L. So in that case, we have to substitute R, that is in millions, 2 into 10 to the power minus 3. Then we have the areas by R square. Here R is given as 1 mm. Then the radius would be 0.5 into 10 to the power minus 3, the whole square, followed by the length of the wire, that is 10 centimeter, then 10 to the power minus 2. So when you substitute all these things, you'll get something like 15.7 into 10 to the power minus 9 ohm meter. So, and then if we convert it to nanometer, then we'll have 15.7. So is this how you got the answer?
Yes, ma'am.
So the answer is 15.7. So we'll move on to the next. What are the probabilities of an electron occupying an energy level 0.01 electron volt above the Fermi level energy at 300 and 500 Kelvin? So here you have E minus EF or EF minus E. You, based on that, you have two equations of finding the probability of where an electron is occupied. So using that equation, you have to find out if the energy level difference is 0.01 at two temperatures, what are the probabilities? And you have four options. So first you have to identify the equation that involves temperature as well as the difference between the actual energy and the Fermi level energy, something which will have a term like E minus EF or EF minus E. So in both cases, what is the probability of that electron in that energy level? So can everybody please start solving? Yeah, if you want help with the equation, I can project the equation for you. So, or have you identified the equation on how to solve this?
Ma'am, it's Fermi direct distribution equation.
Yeah.
And I got option A 0.33 and 0.23.
Okay. Any other answers? Okay, wait for the others and see if anybody else has any other answers. So, when one person has said 0.33 and 0.23 as the probabilities. If anybody else has any other answers, we'll see. Anybody else? Any other answers? So we have to find out the probability of the electronic efficiency, and the energy level is given as 0.01 electron volt above the EF at 300 and 500 Kelvin. So same equation at two temperatures you have to solve. E minus EF will be the same. So in both cases, what is the probability of finding the electron there? Like same energy level difference, but at two different temperatures, what will be the probability? Somebody has noted. So basically, this is the equation that you have to use if E is equal to 1 by 1 plus E minus EF divided by kV into T, where E minus EF is the energy level difference, that is 0.01 in our case, and K is the Boltzmann's constant and T is the temperature. So since it is a ratio, keep in mind that E minus EF and KT should be in the same units. If both of them are in electron volt based units, use that. The other case, if both of them are in the SI units, use that. Since they are a ratio, they'll cancel out eventually. Only thing is that you should keep the numerator and denominator in the same units. So now if you have the equation, can the others please try and tell me which answers they got? Now you have the equation here, you have to just substitute the values and find out. So, so basically we are asked to find out the probability of the electron, 0.01 electron volts above at first 300 Kelvin. So only difference here is that if you see it is substituted, like where I'm converting it into joules and then you see, then first we have to substitute 300 and then we have to substitute in place of 300 we have to substitute 500 Kelvin. So Boltzmann's constant value you should know for doing this. Boltzmann's constant in SI, either both of them in SI or in EV. So in SI it will be 1.38 into 10 to the power minus 23. That is, since the temperature is given in Kelvin, I am going with SI in all cases and I am converting my EV value into joules. That is why I am multiplying it with this 1.6 into 10 to the power minus 19. So first value I got as 0.40456. Similarly, when I am replacing with 500, just only differences here, instead of 300 I'm using 500, I get 0.4422. So the person who got the first option, can you tell me which part like went wrong, just for the for information for the others?
Might be it's during calculation, I
Yeah,
think.
I think you might have probably like substituted one of this in Kelvin and one of this is in electron volt and the other in Joule.
Yeah.
So is it clear for everyone? So please keep note here it is in Kelvin. So substitute both of them in the same unit or substitute in such a way that eventually they get cancelled out and unifies into the same unit. So in first case we'll get 0.40456, in second case you'll get 0.4422. So your answer will be, since we don't have exact values, we'll take the nearest values. In second case it's 0.44. And one more thing, if you note C and D, one thing you can mess up is it's basically the same value, but the order at which they are asked is different. So for 300 we got 0.41 and for 500 we got 0.44. You might get the answers in calculation correctly, but if you are not careful enough, you might end up choosing option D. So please be careful. Whichever order it is mentioned in the question, in the same order you have to go for comma separated values. So first one will be 0.41 and second will be 0.44. So I hope it's clear. We can move on to the next question in that case. Yeah. Somebody has posted something, so kindly guys please speak up, otherwise okay. Yeah, Vidya Sagar has also given the answers. Yeah, presentation not visible. Oh, why so? Somebody has, yeah. I hope it's clarified right now. Okay, yeah. In a metal at some temperature T, the probability of finding an electron above the Fermi level is 1%. The probability of finding an electron at the Fermi level. What is the approximate value of P? Give your answer in Kelvin and use the FEG models. So the same equations that we used previously, right? Sorry. Yeah. Same equation, that is the equation for Fe, 1 by 1 plus E minus Ef by Kt. So here, the next question, we have some metal. At some temperature, we have a probability, say, some value x. And that probability happens at an energy level 0.2 electron volt above the Fermi energy. 1% is 1%, the probability of finding the electron at the Fermi level. So in first case A, you have an energy that is 0.2 electron volt above Fermi level. In B, you have at Fermi level. And the probability of finding the electron at A is 1% of the probability of finding at B. Suppose you have at 0.2 electron volt above Fermi level, you have a value x. Then they have told that x is equal to 1% of y. Y happens at Fermi level. So basically then you will have two equations, and if you equate these two equations, the only remaining variable will be T. So in that case, you have to give the answer in Kelvin. So can everybody try and let me know? Like read the question very carefully. It's a very simple question actually. You have to use the same equation, substitute what is given to you, and then equate and find out T. One is at 0.2 electron volt above Fermi level, one is at Fermi level, and the probability at 0.2 electron volt above Fermi level is 1% of that at Fermi level. So these are the hints, and based on these statements, you have to find the value of T, that is the temperature in Kelvin.
Hello, ma'am.
Yeah.
I'm getting 505 Kelvin, but it is not in the option.
505. Okay, so let us wait for a few minutes and we'll get into the solving. Let's see if anybody has any answers from the options. Yeah. So let us wait for one more minute and then we'll see. Yeah, so we'll see. So basically, Fe is equal to 1 by 1 plus E minus Ef by K into T. So where T is in Kelvin, so we have to substitute E minus Ef, that is 0.2 into 10 to the power 1.9 to 10 to the power minus 19. You have to do to convert it into joules, and Boltzmann's constant you have to use 1.38 to 10 to the power minus 23. Okay, so first we'll solve for at Fermi level. At Fermi level, what happens? E minus Ef is equal to 0. In that case, e to the power 0 by k into t, e to the power 0 by something, e to the power 0, 1 by 1 by 2. So basically, in the second case, at the Fermi level, the value of Fe is 0.5. Now we move on to the first condition. That is at zero point 0.2 electron volt above the Fermi level. That is when E minus Ef is equal to 0.2 electron volt, then that probability is 1% of this value. 1 divided by 100 into this value is equal to the Fe at 0.2 electron volt above the Fermi level. So given that the probability at 0.2 is 1% of that at Fermi level, so at Fermi level we got the value as 0.5. So 1% of that value is what we will get at 1 by 1 plus e to the power 0.2 by kt. 0.2 means that it is 0.2 electron volt above the Fermi level. So when you substitute k as 1.38 into 10 to the power minus 23, when what we will get, you have to substitute all values, that is 0.01, 0.5, e to the power 0.2 into 1.6 into 10 to the power minus 19, 1.38 into 10 to the power minus 23, and finally t. So once you get this equation, you have to equate them and find the value of t. E to the power some constant value by t you will be getting, and then you have to convert them into logarithm, and then if you take, you will get the value of t. So you get it as 438.0070. So can somebody else got some value in the range of 500, right? So where was the calculation issue? Hello? Yeah, okay. 0.01 multiplied with 0.5. I got the answer as 0.5, not 5. Okay, so that is what. In the question, if you see, like, let me take, if you see here, where is my cursor? So if you see here, at Fermi level, we have some value x. That x value is 0.5. The second condition they are telling is something we got at x, and for at y, it is 1% of what we got at Fermi level. So that is the first part. First part, you just do something, you get the value for Fermi level. Okay, that part is done. Then see this sentence. Probability of finding an electron zero point 0.2 electron volt above the Fermi energy. That is, when E minus EF is 0.2, then we will get some Fe value. That Fe value is 1% of this value. So is it clear? So first we have to find out the value at Fermi level. We got some value 0.5, we keep it aside. Then we go back to the statement. There is another Fe value, and that Fe is for E minus EF is equal to 0.2 electron volt. And this new Fe value is 1% of what we got at Fermi level. That is why we multiply 1% into 0.5. That is why we multiply this 1% into 0.5. Actually, this is the value of 0.2 electron volt. Like when the energy is 0.2 electron volt above Fermi level. That is why we substitute 0.2 here. So is it clear? Yeah. Somebody had mentioned in the chat box like why this is multiplied. This is because they are telling the value at 0.2 electron volt above Fermi level is 1% of what we get at Fermi level. This 0.5 is for Fermi level. 1% of that value is the Fe at 0.2 above Fermi level. So in that case, and then you substitute everything in joules, and once you get this, you condense this equation, and finally you will end up with some constant value here, 1 over here, 1 plus some constant value by e to the power something t. So what happens? Then we have to take log on both sides, and then we'll get the t value. Is it clear? Yeah. Okay. Yeah, I hope that's clear. Then we can move on to the next question. What is the dependence of density of states on energy in a three-dimensional solid? Density of states increases linearly with energy, increases as the square root of energy, as the square of energy. Density of states is independent of energy. Actually, we solved one question in the starting. So in that question, if you remember, where was the energy term? Was it in a square or was it in a root or what was it? Dependence of density of states on energy in a three-dimensional solid. So from the first equation that we used, you can tell me the answer. Density of states equation was there. It had many constants, etc., 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 and so on. And finally, it had some term related to the energy value. And how was the energy value? Was it a root or was it a square or cube or was it linear? Can anybody tell me?
Square root of energy.
Yeah. So this is basically the equation that you are using, and here you can see if this term it is in the root of EF. So we go for the option B, which says that increases as the square root of energy. So next is the resistivity of two metals A and B are 16 and 56 nanometers respectively. Two resistors are fabricated from A and B. The length are same, but dia is different. And how are they different? Diameter of resistor made from A is twice the diameter of resistor made from B, which means that dia of A is 2 times dia of B. Then what is the ratio of these resistance? And the ratio should be RA divided by RP. So can you guys start solving? So basically it is the same equation, resistivity, resistance, length and dia. R is equal to rho into L by A. Only thing is in the area term we have pi r square. But that pi r square here has a ratio. That is RA or dA is twice of dB. So based on this statement. Then if you convert both of them into dA and dB, that ratio value you can get. You have to find the answer for RA by RB. So can you try?
is 0.071.
Okay, someone has got 0.07. Okay, we'll wait for the others and see.
Hello, ma'am.
Yeah.
I'm getting 0.0714. That means here it is closest to option A.
Okay, yeah. So both people here have got the same value, right? Yeah. So R is equal to rho into L by A, and RA will be rho A, LA, A times RA. So instead of the area, we'll be substituting pi by 4 d square. So we have something of dA square and dB square. We separate two separate equations. And then length of both are same, it is given. Then diameter of A is twice the diameter of B. And resistivities are given as 16 and 56 respectively. Then while substituting RA by RB, this row values we have to give, pi by 4 gets cancelled, LA, LB gets cancelled. Then dA we have to substitute as 4 times dB square. So it will be 0.0714 RA by RB. So I hope everyone got the answer on how to do this. Yeah, I hope it's clear. I think we can move on to the next. Yeah. Okay. So now we have a few again we'll move on to a few logical questions again. So the process of increasing carrier concentration by adding impurities to an intrinsic semiconductor is called dash. It's a very direct question. So the process of increasing carrier concentration by adding impurities to an intrinsic semiconductor is called dash.
Doping.
Yeah. Okay, that's correct. And now at absolute zero temperature, the conduction band of a semiconductor is dash.
Completely empty.
Okay, anybody other answers? At absolute zero, conduction band is dash. Completely empty. Absolute zero temperature, there will be no thermal excitation from the valence band to conduction band. Therefore, the conduction band will be completely empty. So, which of the following is an example of a 3-5 semiconductor? Something that involves a combination of a group 3 and group 5 element.
Ma'am, it's gallium arsenide.
Yeah, that is the correct answer. So one is a group 3 element, one is a group 5 element. So we have a combination as gallium arsenide. So that is the questions for today. So I hope the questions were clear to all of you. So once again, I thank all of you for your attention, and you can post your additional questions either in the discussion forum or mail me at santra.pmrfiatm@gmail.com. So in that case, do you have any other further queries? Like anything that you want to know or how you want to make changes to this session or any inputs if you have, you can please tell me now.
KT value can be taken directly at 300 Kelvin, 0.026 electron volt.
Okay.
In the ninth problem.
Okay, instead of substituting. Yeah, if you know some shortcuts like this from your previous things, you can use that surely. Yes. Yeah.
but somehow I'm not getting the answer that you gave, but maybe I
Okay.
did
Yeah,
some mistake.
you can try once more in the mean like whenever you are free, and in case you are not getting the answer till then, like even up before the next class, you can mail me so that I can maybe write up the solution on a paper and send a picture to you or something like that. Yeah,
Fine.
yeah.
Thank
So anything else?
No, madam.
Yeah. So in that case, thank you everyone for joining. So I hope that you guys will be present for the session on the coming Tuesday as well, in every other Tuesday until your exams are there. We'll be waiting for live sessions like this. So thank you everyone for joining. Hoping to see you next week. Thank you so much. You guys can leave now. Thank you. Yeah.
thank you.
Yeah.